Hello everyone, and welcome to this session in which we will introduce decision trees. We will first see how decision trees are interesting tools to extract information from a labeled dataset. I will then present the process of building a decision tree for supervised learning problems to deal with both the regression and classification cases. If the general construction is easy to understand, we will then go into detail by studying the different choices that determine the construction of a tree, the splitting criterion, the stopping criterion, and the choice of the different hyperparameters which have an influence on the predictive performance of the algorithm. One of the great advantages of decision trees is that they can be applied to input variables of different types, such as continuous and discrete variables. An essential step to use a decision tree in a predictive context is the pruning step of the tree to improve its predictive performance. We will summarize all these elements by presenting the complete algorithm of decision trees. First of all, what is a decision tree? In a general sense, a decision tree is a tool that allows you to make a decision by asking a sequence of questions, the choice of each question depending on the set of previous answers. We encounter decision trees in everyday life. For example, you may ask yourself the question, should I watch this video on decision trees? So here is an example of a decision tree to answer that question. A decision tree looks like this and is read from top to bottom. Each cell corresponds to a question, called a node of the tree. Each branch, starting from a given cell or node, corresponds to a possible answer to that question. Let's take the first box with the following statement. Decision trees are not difficult to build. To proceed through the tree, you must choose whether this statement holds. If you think it is true, you will follow the right-hand branch, and if you do not agree, you will follow the left-hand branch. Notice that the left cell has a different shape, which corresponds to the fact that no branch starts from this cell. When we reach such a cell, the journey through the tree ends. This particular type of tree node is called a tree leaf. Leaves are nothing more than the terminal nodes of the tree, that is, the nodes for which no questions are asked. When we arrive in such a cell, we get a decision. Here, this decision, in response to the initial question, should you watch this video about trees, is positive. Indeed, after watching this video, you should know that a decision tree is not difficult to construct. If you have arrived in this leaf, it is because you think the opposite, therefore watching these videos again will be useful. Let's go back and assume that you know enough about trees to think that they are easy to build. This brings you to the right-hand cell, where you are confronted with a new statement, random forests are classical forests that appear and disappear spontaneously. If you think that this statement is true, you will choose the right branch, which encourages you to make the decision to watch these videos. Indeed, spontaneous appearance and disappearance are not characteristics of a random forest. Our object of study is much simpler and does not disappear spontaneously. Conversely, if you disagree with this statement, you will go through the left branch. The decision tree then asks you a final question. Did you answer the previous question randomly? If your answer is positive, the tree advises you to watch the videos. Even regarding random forests, random answers are not encouraged. Conversely, if you answered knowingly, you are potentially ready to take the quiz to verify that you have mastered the fundamentals of decision trees. We have just seen an example of a decision tree. A sequence of questions is asked in order to make a decision. This decision tree was built by hand, using my own expertise. I used my knowledge to build such a tree. It was not very complicated because the tree you see here is shallow. It contains at most a sequence of 3 questions. We say that the tree is of depth 3. Building a more complex, i.e. deeper tree with more questions in order to model more complex phenomena is tricky. In particular, it is often difficult to deduce a complex decision tree from a discussion with an expert. The expert has not necessarily formalized his entire decision process. There is therefore an interest in building decision trees from data and not from knowledge. But is it possible? Is it possible to build decision trees without using expert knowledge, but with a collected and labeled dataset, which would allow to determine the best question to ask within the tree? In other words, can we collect data automatically to create a decision tree without specific knowledge of the application domain? Fortunately, the answer is yes. Here you see a decision tree that was trained on a data set from 1990 California census of real estate data. An observation of this data set corresponds to a set of houses, a block. The input variables are information about this block: median income of the occupants, average number of rooms, and the variable to predict is the average price of a house in this area. In this context, the decision tree seeks to predict the average price of a house within a block according to its characteristics. Let's take the first cell you see at the top of the tree. It tells us that the question to ask, the split, is based on MEDINC, the median income of the people living in the block. If, for a given zone, the median income of the people in this zone is less than 5, corresponding to a salary of $50,000 per year, the path within the tree continues on the left. The left-hand branch corresponds to areas whose inhabitants have a lower income than the right-hand branch. Logically enough, the values of the houses in the left branch is 170,000, threshold at 1.7, which is lower than the right branch, which is 330,000. If the decision tree stopped at this level, depth equal to 1, we would predict the price of a house based only on the median income of the inhabitants of the given block. Fortunately, we can obtain a more accurate decision tree by continuing our sequence of questions. Note that here, a question concerns an input variable and is of the form, is this input variable less than or greater than some threshold? At the first level of the tree, the variable is the median income and the threshold is 5. In the next level of the tree, the left branch is also based on the median income. If it is less than 3.07, we proceed to the left branch, otherwise to the right. Note that by following the left branch, we arrive in a leaf of the tree. No arrow starts from this box. The decision tree then provides a prediction of the price for a house whose average income of the inhabitants is less than 3.07. In this case, the value of the house is predicted to be $135,000. It is also possible to read the number of observations falling in this leaf, i.e. the number of observations in the dataset with the characteristic of this node. Here, 7,860 areas have inhabitants with a median income below $30,700. The squared error in this leaf is also provided. It is 0.561. It corresponds to the variance of the observation in this leaf and allows to evaluate how close the different observations of this leaf are in terms of labels, i.e. here the price of the house. A low value means that the house prices are quite close within the leaf. Here, the error is the smallest among the errors of the other nodes of the same level, which means that the prediction in this leaf is, on average, more relevant than the prediction of the other nodes of the same level. Note that other nodes in the tree cut according to other variables, such as the average occupancy rate for the 2 leaves in the third level, for example. This decision tree could have been constructed from expert knowledge, such as that of real estate agents at the time. As already mentioned, it is often difficult to build a decision tree based on business discussion only. Here, this decision tree was built with data without any business knowledge. To do this, we needed data on the real estate values of the houses, output variable or label, and on the characteristic of these houses, the input variables. A common practice to validate this tree is then to present it to experts to get their opinion on the choices of variables and the structure of the tree. In this module on decision trees, we will see how these trees are constructed. From now on, when we talk about decision trees, we refer to such trees built from the data.